Hey everybody, welcome to another episode of Problem Solved, the IISE podcast. I'm David Brandt, and this episode is brought to you by the IISE Modeling and Simulation Division. Andrew Collins, a professor of industrial and systems engineering at Old Dominion University, is going to talk with two professors from George Mason University about the growing use of digital twin modeling and how it serves as a predictive tool for physical systems.
Hello, my name is Andy Collins from Old Dominion University, which is a university in Southern Virginia. I'm here today with Jay Xu and Chun-Hung, both from George Mason University, which is in Northern Virginia. Jay and Chen, could you introduce yourselves, please?
Andy, thanks very much for the invitation. It's a great pleasure for us to have the opportunity here to talk about our research related to digital twin and learning. I'm currently associate professor of systems engineering and operations research in the George Mason University. So my research area focuses on stochastic simulation and digital twin simulation and analytics and optimization using simulation and digital twin. I received my PhD in industrial engineering and management science from Northwestern University in 2009. After I graduated, I worked for United Airlines for 2 years in the enterprise optimization department, where I spent a lot of time developing simulation models for United Airlines and user simulation to support a strategic decision-making for the airline. So it's a very good experience for me to see how simulations and increasingly we see digital twin being used to support highly important decisions in very complex environments. Since I joined George Mason in 2011, I have been working on many simulation and digital twin related research projects sponsored by different agencies such as the National Science Foundation and the Air Force Office of Scientific Research. And specifically, the framework we use to integrate machine learning and the digital twin has been sponsored by the Dynamic Data and Information Processing Program of Air Force Office of Scientific Research. The support from the program director, Dr. Eric Blasch, has enabled us to conduct the research that we hope to talk about today. I'm also currently the president of Informs Simulation Society.
I'm Chun-Hung Chen, a colleague of Jay Xu. It has been a great pleasure working with Jay Xu for several years at George Mason University. I got my PhD from Harvard University in 1994. And before joining George Mason, I was a professor at University of Pennsylvania. My research area is also in simulation and optimization, but with focus on how to make simulation optimization much more efficient. In particular, I developed a very popular technique called optimal computing budget allocation, or CBA, which has become the state of the art for simulation optimization. I have been on the editorial board for several prestigious journals and sponsored by several funding agencies, and particularly the Air Force research, Air Force system research. It has been very nice to be here and to talk about simulation and digital twin and learning.
Excellent. Glad to have you both. The reason for this podcast is that we're going to be talking about digital twins. So would one of you mind just explaining what a digital twin is, please?
Okay, so I'd be happy to share with you my opinions on what is a digital twin and its differences between what we have historically referred to as a simulation and nowadays digital twin. People have been using computer models to represent the physical systems and use it as a predictive tool. Since the inception of digital computers, I would say, people have seen this possibility. What makes digital twin now different from what the people have been doing using computer models, I think, are the pervasive use of sensors and the availability of dynamic data input to reflect in real time what is happening in your environment, what is happening inside the system, and to assimilate such dynamic data input into a computer simulation model. So you could use the simulation model in real time to evaluate how the system is behaving, and if you take certain actions, what's going to happen in the future, given the current circumstances of the system. So I think that's the defining characteristics of a digital twin. You are making the computer model reflect the current state of the system, and because of that capability, we could possibly use it to support the real-time decision making.
What are the differences from what I would call traditional simulation, like discrete event simulation, etc.?
That's an excellent question. So indeed, in my view, there are many similarities between traditional simulation, such as discrete event simulation, and today what many people refer to as a digital twin and their applications. I think if we look at how traditionally simulation have been used, we will be able to grasp the main difference between today's digital twin and its applications and the traditional way simulations are used. So in the past, we say simulations can be used to answer what if questions in the design and the planning phase of a system. Or at least if it is operational planning, we'll talk about maybe in a day or next week or next month. It's not real time. We use simulation to look into the future, how the system would behave given certain forecasts of what future would look like. And then we could use that predictions to change our design and see if we could improve the performance of the design or if the design is going to meet up the design specification. So the focus is on design and planning. So that's for traditional historical simulation. And with digital twin, there are two things affecting how we use digital twin differently from traditional simulation. The first one is the ability to assimilate dynamic data input. So it's no longer data sets, right? It's no longer historical data sets that represent what past looks like, right? Instead, it's currently what the system looks like and what are the conditions that the system needs to respond to. What is the event the system needs to respond to? So it represents now, the present moment. And secondly, with the explosive growth in computing power, we can now execute in real time very complex simulations that in the past could take us days or even weeks to run, right? So because in the past, you have to take so much time to run simulation, using them to support real-time decision making is not possible. But now with digital twin, even though it's still computer simulation, let's make this clear, right? So it's still computer model representing how the physical system, the real world system operates, right? So that's fundamentally, I don't think that has changed. But what has changed is now the system represents what the real world system is like now, right? And because of that capability and the computing power we have, we can use it to predict the real-time consequences of any actions. So to me, that's a huge difference between how traditional simulation is used and what we can now do with digital twin.
So I think you've touched on this a little bit, but I was just wondering, how can you use digital twins to help make better decisions about the system?
Yes, I'll be happy to elaborate a little bit more on that. Real-world systems are very complex. We cannot expect to write down nice closed form equations to tell us if we take action A, what's going to happen to the system's performance, right? If we look at the key performance metrics, right? If I take certain action, what will be the XYZ like in terms of different performance metrics? So we have to rely on complex computer simulation models. And in this case, we would call them digital twin simulation models to let us know the consequence of taking certain actions, right? And because of that capability to look into the future of my action, given the current circumstances we are in, then a direct step forward is to say, if I have several actions in mind, I don't know which one is the best. I could ask my digital twin to simulate these alternative actions and tell me which one is the best. Or maybe several of the top decisions, some of the best decisions, then I can exercise my quantitative judgment to select the best decision I want to take, right? So this is highly desirable for a decision maker facing a very complex and uncertain, complex system and uncertain environment.
Part of your research you've been proposing is the integration of machine learning and digital twins. Could you just talk a little bit about that for us?
Yes, maybe I can use example to illustrate what we have been working on in this regard. I've been working with some national lab scientists and power industry engineers to study how we can use digital twin and the machine learning together to help them plan for major weather events such as storms, right? And so power systems have engineers have been using many simulation models to try to predict what's going to happen to the power grid if certain elements of the power grid is taken down by a storm, such as a transmission line or a transformer substation. But these models, first, they are time consuming to run. And secondly, this is also called a contingency analysis, right? Contingency planning. But there are so many different contingencies that they can plan for. And they have limited time to look across all different contingencies and plan for each one of them, right? So it's impossible to exhaust all the contingencies, even though you have a model that in theory you can use to go across a huge number of contingencies, right? So what we propose as a solution is we could combine the power of machine learning using the data that we generate using this simulation model offline before a major weather event is going to happen. We could extract knowledge from this offline generated simulation data using machine learning. So online, when the weather comes in, when we have a short-term weather forecast that gives us very good information, we could forecast how the power grid will be affected by the storm, and we would be able to feed such information into a machine learning model to tell me what would be my best mitigation actions. Just using machine learning would give us a good starting point. But don't forget, we still have access to these high fidelity simulation models or digital twins, right? So now we could play our game of a digital twinning simulation and this digital twin based decision support, right? So we could feed the dynamic data into a digital simulation, and we can take what's the actions recommended by machine learning models and see if they are indeed good actions. And this is where our research differs from traditional machine learning based problems, because we have access to these digital twin simulations, right? So we could try to improve upon what machine learning tell us are the good mitigation actions, because machine learning are trained on a limited amount of data, right? It will never be able to exactly replicate what is happening today. But using digital twin, we know what is happening now, and we can simulate and find the best mitigation action. But it has to be done in real time. So you cannot just use digital twin to go across all possible solutions. Instead, machine learning help us to zoom in towards the most likely effective mitigation actions. And our core research contribution is to come up with a rigorous and also highly computationally efficient framework to say how we do this integration between machine learning and the digital twin simulation.
I want to add something what Jay just said is that the digital twin is very powerful to replicate what the system is running, and then it can also be used for the future planning or the mitigation of any possible event. However, nobody can perfectly predict the future. So offline learning is important, but online is also very important. When we observe the real forecast, we still have a little bit of time. We don't have much time, but we need to come up with a good decision or a good mitigation strategy. At that time, we call it the online learning and simulation. And what to do that in the best way and a very efficient way. I think that is we come up with the very nice research and methodology to accomplish that.
So I think you've covered, why you don't want to just use simulation on itself. And you've also covered why you don't want to just use machine learning. And you talk about online and offline learning. Could you just add for the listeners just a bit more clarification on what you mean by online and offline learning?
online and offline, the main difference is that offline, we have much more time. So thinking about that, I want to plan something for tomorrow. So until tomorrow, I have some time, not infinite time, but at least we have many hours until tomorrow. And that's what we call offline. So offline, we have much more computing budget, and then so I can think about what are the we can simulate many different alternatives in order to come up with a good decision. However, the challenge is that before tomorrow, I cannot perfectly predict tomorrow's scenario. So I just need to guess. So we can try to think about some possible scenario for tomorrow, and then come up with the good decision for those scenarios. So that's the offline part. So offline, I have more time, but the future is not perfectly predicted yet. Online is the point that I have observed the real-time data, or the real-time weather, or the near future weather that I'm pretty confident. However, I don't have much time. The time to make a decision is very short, and that's why we call it online. And so the methodology will be quite different for these two phases. Again, offline, I have plenty of time. Although not unlimited, but all the information is not totally clear, not totally perfectly predicted. Online, I get the information, I get the real-time data. However, I don't have much time to run the simulation or even for the optimization. So those are the main difference and the different challenges.
Okay, thank you. I think, so that explains why you can't just use offline or online on their own. And that's, again, like you're using machine learning and simulation and combined, you need to use online and offline combined. So you've created the sample framework, which combines both simulation and machine learning. I wonder if you could talk about, in terms for a layman that they could understand, could you talk about this sample framework?
Yes, I'd be happy to do so. And so sample is a general framework that we propose to implement this idea of combining machine learning that were trained offline using simulation data and online simulation where we observe what the system needs to respond to in real time and use digital simulation to generate new data online, and then combine these machine learning predictions with online generated simulation data to support decision making. So in a layman's term, if you would think this is the layman's term, we use a Gaussian mixture model. Or you can think of this as a very flexible statistical model that would allow us to have multiple sources of information to be modeled, including we could have multiple machine learning predictions and the digital twin simulation that we can use online. And we made several key methodology innovations to extend the traditional Gaussian mixture model framework for this new paradigm of offline simulation and online training. That's more technical. I'm going to skip over. But in a nutshell, what the modeling framework does is to use the machine learning predictions to quickly separate alternative actions into several groups, right? So we could say these are the candidates we should focus more on. These are, maybe they still do well, but we're not so sure. So let's keep them on the back burner. And then there's another group we say most likely they're not going to work out. So you may want to take a look into it if you have time, but don't worry. So that's how we use the machine learning to do this quick screening of potentially a huge number of alternative actions. Then the role of online digital simulation, digital twin simulation, is to obtain more accurate data because it's a digital twin, right? So obtain more accurate data, and then we can update our knowledge about the performance of different actions based on the original machine learning predictions and this dynamically generated digital twin simulation. And this Gaussian mixture model framework would allow us to combine these different sources of predictions into one performance estimate of each estimation together with this uncertainty. With the uncertainty we have in this estimate, you can also see how confident we are, right? So uncertainty and confidence are related. And so this would let us know if we need to run more simulation, if time allows, or if we are out of time, we have to make a decision now, we can make the best using the computational resources and time we are given. So hopefully in a nutshell, that gives you some rough idea how mathematically this framework works.
Yeah, thank you. Thank you, Jay. That was very helpful. So I got an idea there. So we're all academics here, and we like to have conversations about theory. But one of the questions that has to come up is like, how does this sample framework work in practice? I mean, how does it perform?
Yeah, thanks very much for the question. So indeed, whenever we propose a computational approach, we want to see numeric empirically, right? So how much computational efficiency we're able to achieve using sample. So we have conducted fairly extensive experiments in our studies using both benchmark test functions that have been used widely in simulation optimization literature, and also several case studies that are motivated by important real-world problems and also based on test cases that are widely used in their own application domains, including healthcare, how we can use digital twin simulation to help guide the allocation of scarce healthcare resources. And you mentioned pandemic, that's very important, how we want to prioritize the allocation of scarce medical resources when we are responding to pandemic. We apply this to power grid setting, and which can also be generalized to the protection of important infrastructure systems against any natural or man-made disruptions. And we also applied it to manufacturing, and more specifically semiconductor manufacturing setting, how we can change the resource allocation and come up with new production plans in response to either machine breakdowns, or if you have some new demand requirements, new product demand requirements, how you can quickly come up with a production plan that would maximize your productivity of your manufacturing system. And in general, these sample, of course, because we are combining both machine learning and the digital twin simulation, and we would expect the quality of the predictive accuracy of your machine learning model would have a considerable impact on the actual performance of sample compared to if you just use a traditional simulation optimization approach. The use of a machine learning is what gives you the edge to outperform the traditional simulation optimization approach. When we could have fairly accurate machine learning prediction models, we have seen the speed up factor if we want to have a certain confidence in the decision we are making, right? We could speed up the amount of a digital twin simulation you have to do, or we reduce the time by several folds, right? So 5 times, 10 times, we have seen that. When you do not have a very accurate machine learning predictions, it could be just maybe twice faster than if you just rely on simulation optimization. No surprise, it's problem dependent. But I think a very important observation we have obtained through our experiment is no matter how the machine learning prediction quality varies, of course, it cannot be totally off, right? This is a pretty robust framework that will be able to work nicely with machine learning models, which could be actually quite crude, can be very simple to use. And that's of mediocre predictive quality, but still, because we integrate this with simulation optimization, so we're always able to see considerable computational gains using the different sources of information, even though by themselves, if any of the information source we use them on its own, it may not give us the computational efficiency and the quality of the decision we would like to have. But together, once we integrate them using this mathematically rigorous and efficient framework, we have seen tremendous performance improvement and a lot of potential for real-world application of the sample framework.
All right. So thank you. So we've been on a bit of a journey. We've talked about, what digital twins are, how they're different from traditional simulation, how you can integrate machine learning, and how effective that's been for you. So just to wrap up, I think one conversation we should have is, what is the future for digital twins? What does that look like?
That's an excellent and also a very challenging question, right? So we're looking into a crystal ball trying to make bold predictions. I think one thing most of my colleagues and the practitioners, we would agree is that there's a very bright future for digital twin, and whether you want to call it the digital twin engineering or just a digital twin research. There's a bright future for us. But opportunities arise together with challenges. one of the biggest challenges, obviously, is how we could develop computer simulation model that would be able to assimilate dynamic data input on the fly as they come in and run high fidelity simulation at a speed fast enough to support the decision making, right? So sample and all the analytics work we have done makes this decision process an efficient one. But if we do not have high fidelity digital simulation, that's not possible. And second, if any single run take a long time to finish, then forget about all the analytics we could possibly do, right? So first, I would say the first opportunity and also challenge is the engineering part. How we could develop digital twin simulations that will be able to apply successfully in the real world on a wide range of decision-making tasks. That's our first opportunity and challenge. And the second one is data. And digital twin relies critically on the capability to incorporate or assimilate data that comes from sensors embedded in the real world system, the physical system or cyber physical system, right? To reflect what the cyber physical system, the current state is, right? And this is not a trivial task by any means, right? So how we can get this process done efficiently? There are hundreds and thousands of even millions of sensors embedded in complex cyber physical systems. How could you pull all that data into a digital twin simulation model, process them, and use them to parameterize the simulation model you have, and then you can start running your simulation, right? And so this is a huge demanding task. And third, again, this comes back to how digital twin is envisioned to be used to support real-time decision making. We have to do things online in real time. We no longer have the luxury of a traditional simulation research where we say, if we have to run the simulation 1 million times to give us the confidence we need to make this decision, let's just run it 1 million times, right? So we are in a highly constrained computational budget and computational time setting, right? So this puts on new demands on the development of highly efficient and rigorous analytics methodologies to support decision making using digital twin. And so Professor Chen, he's the inventor of the very popular technique OCBA he mentioned in the past, optimal computing budget allocation, that has been highly successful for traditional simulation optimization where you have a limited computational budget. And now we are really trying to push the envelope of what OCBA can do with this new sample framework to combine the strengths of machine learning with the strengths of OCBA to help make digital twin a powerful analytics tool, a decision support tool.
Okay, so thank you both for talking to me. I've really enjoyed this conversation. Appreciate your time and wish you all the best in the future.
Thank you so much, Andy, for your invitation.
Thank you. I'm glad to be here. Thank you.
You've been listening to Problem Solved, the IISE podcast, a production of the Institute of Industrial and Systems Engineers in Norcross, Georgia. We hope you'll share this and other Problem Solved episodes with your friends and colleagues. Learn more about sponsorship and advertising opportunities, as well as how you can become a member of IISE by visiting podcast.iise.org.